Okay, hi everyone. Good to see you. Today is the last lecture before we hand it over to you to present your projects, and we have a lot to achieve today because I'll be touching on the issue of numbers and energy, and there's a lot of interesting ways to look at that problem for a personal level, from a global level, and really, even though I'll be talking about the specific example of energy, I think it tells a larger story, hopefully, of how numbers could be like something that goes across different scales. And I hope you'll see that it's really like the thing that could convert between lots of things we're interested in. So that's the plan for today. And I'll jump directly to the first example from which we could build. And that is the question of how much energy is humanity consuming. And as a result of that, the fact that we're burning or adding so much, creating so much heat through that energy, could it be that directly, just by the energy usage of each one of us, we're heating the Earth? Okay, without talking now about greenhouse gas, greenhouse effect, just from the fact that we're using so much energy that was, in the somewhere, somehow in fossil fuels, and just that heat that is being released, how much does that heat the Earth, and how does that compare to the other things that we're doing? Questions clear? So let's jump into trying to do that. So what would be if I want to do that, the first thing I need to know is something like, is how much power humanity consumes. So I'm guessing that if I was asking you that, what?
Was that not given in the simulation you gave us? Like, kind of?
It's related to things that you got in the exercise. Therefore, I'm also doing that because that hopefully would tie up all sorts of things that you succeeded or succeeded less in doing. Also in terms of like estimating how much carbon emissions we have and all of those things. I hope everything would tie up together today. So if I'm giving you such a question, if you're like me, it's very difficult to have an intuition for something so big and global, because the world is big. How do I even have a handle on that? So a way to go about it is very often to try and bring it from the global to the personal. Okay, to something that we have better intuition on, because I give you a value for this. Maybe it's in the giga, maybe it's in the tera, maybe it's billions, millions, trillions. Who knows how to handle that? But if we talk about a person, usually it's something that we have better intuition for. Okay, so a very common trick is to say, okay, instead of asking that, I could convert it to how much power am I using? And to make it even more concrete, let's take something like electric power. A person consumes on average.
On average, what time span?
So when I'm talking on average, it doesn't depend on the time scale. So you could say, over a year, how much energy, and divide it by year, or over a month and divide it by a month, or over a day. We're not talking about the seconds or something like that, which could fluctuate a lot.
Yeah.
Good. Anybody has some intuition for that? If I was trying to get the value regarding that.
I'm checking the electric bill.
Yeah.
Okay, so one way to go about it is to check your energy bill. That's a great idea. Maybe we'll get to it in a minute. You had
That's also what I did.
Okay, so if you know your energy bill, that's useful. Before going to your energy bill, any other ways to get some context for such a question?
We can try to estimate the effect of the electricity we use. For example, oven heating food, so we can try to estimate temperature and.
Okay, so we could connect it to this thing about heating stuff. So we'll also do that today in another way. So that's also good. Great. Any other ways?
The power of each electrical machine we use at home. So how much does the refrigerator takes and a microwave.
Fantastic. So you can go to all sorts of appliances that we know we're using. So what would you say are characteristic values of what you're using there?
1,000 watts? 1,000 watts, right? In watts.
Hundreds to thousands of watts.
Hundreds to thousands of watts. Good. So, okay, so we now have one kind of context. Maybe another context you could put in is like remembering something about a human. You remember what's the power of a human? 100 watts. We looked at it. It's a good number to carry in your head. So what do you think? The electric power is more or less than a person, or about the same? More. Okay. So we know we want to go above 100. Okay. So now, okay. So we already have, just from our basic intuition, something to guide us. But then if you had to know, how would you usually do it? I'm guessing today the way you do it is you just ask, ChatGPT or some LLM or something like that. So maybe you try to do it for a minute and see what value do you get.
The average like appliance?
Yeah, the average electric power used by a person in Israel. And I'm doing it this way because I'm guessing that today that's how you try to approach things in the fast. So on the one hand, it's good to carry things in your head, but if you're tempted like me, you'll probably use that amazing tool that we have available to us. So we want to recreate or simulate this situation that's as realistic as possible. Anybody has a value for me?
30 kilowatt hours per household per day.
Okay, that's good, but I want to get like something in units of power, like average power. So otherwise it's a bit tough. I don't want to do unit conversion once again. So you could ask to get value in watts, which is the thing we're after.
10,000 kilowatts per year per household.
Okay, that's again kilowatts hour per year. I can do the conversion, but I want them, already to help you as much as possible. So you could ask to get it in units of watts.
380 watts.
What?
380 watts per person.
Okay, anybody get something else?
10 to 15.
750 watts, I guess, per person.
Okay, so we're getting, several hundreds, 750. So when I get, such values, I would usually round it up. So we're getting on the order of 1,000 watts or 1 kilowatt.
Per person per day.
Per person, per day.
No, it's
Per year. Average use per year.
Okay, so the nice thing with power is that it is independent of the unit of time. So it's not per day, it's not per hour, it's not per year. It's like 1 kilowatt. That's the rate. It's a rate, it's not an energy. Okay, it's always confusing these things, right? So it's a rate, 1 kilowatt tells you the whole story. And now we could go back to this intuition that we had before. Okay, what did we have? We had the appliances, and people said, appliances usually a few hundred watt, like appliances that really uses electricity, like air conditioning, heater, blender, stuff like that. Not something like, just uses, that's hardly uses any energy. So that's in the hundreds or a few kilowatts. So great. So it's as effective like using one appliance continuously all the time. Okay, that's one way to check your intuition. Another way to check your intuition is to say, okay, a person is 100 watts, and we know the stuff we're using electricity is significantly more. So 1 kilowatt, we see it's roughly at the right order of magnitude. Okay. Now, if we want to do like a quick sanity check from a different angle, is the energy bill, right? So if I'm using 1 kilowatt, in order to convert to do an energy bill estimate, I need to know also the cost of electricity. How much is the cost of electricity?
0.64.
Right, so somebody knows the electricity bill. So it's somewhere between half a shekel to 1 shekel per kilowatt hour, or globally it's between 10 cents to a few tens of cents per kilowatt hour, like 0.1 to point few, say dollar per kilowatt hour. And I won't bore you with that, but you can then take the fact that if you're using 1 kilowatt, so that's 1 kilowatt hour per hour. So you need to multiply by the number of hours, 24 hours, 30 days, you get a monthly bill, and you can compare it to this, and you'll get something, and it should be of the same order of magnitude as what you're paying. It would come out, if you try that, it's a nice thing to verify. I'm guessing it would be significantly more than your energy bill, your electricity bill. How come?
Again, the price would be.
I think if we do the calculation, you'll get something that's somewhat more than your usual electricity bill. So maybe because you're students who are poor and only the professors could pay a good electricity bill. But it's also because here we're taking the average over your life, and actually your energy bill, part of it you pay at home, but actually the Weizmann Institute is paying a lot of electricity bill because you're spending half of your day around here, and also the government pays also, or also so your supermarket pays for some of the electricity bill, all sorts of other things. So when you do this, it comes out to somewhat more because this includes all of the things happening in the economy. Yeah.
So that average, just to validate, the average that we just spoke about 1 kilowatt, also takes into consideration food production, manufacturing.
Everything that's electricity. Okay, electricity. It doesn't take into account other stuff. We could talk about it in a minute as well. Good. So now that we have that, we could go and ask about, before we answer this thing about the heating that I started with, we have some angle. Let's look for a second, okay, how much electricity in total does that require humanity to produce? So if I'm taking 1 kilowatt hour, this was per person. I want to ask myself, how much electricity in total are we producing? So I could take that value, 1 kilowatt per person, and multiply by the number of people, right? How many people?
8 billion.
8 billion, let's make it 10 to the 10 billion persons. So that means that overall, I have 10 to the 10. This is, in terms of watts, this is kilos, so 10 to the 3. So overall, 10 to the 13 watts.
But you didn't take, this is the average for Western, not all.
Very good. So you can now ask yourself, this was like taking a rough value, let's say characteristic for a Western country, and multiply it. And you can make the correction to what, how much are in the global south, in the global north, etc. That's good. That should be done, let's say, if you want to pay the bill or something like that. I would say in terms of the order of magnitude, it wouldn't move us from 10 to the 13 to the 10 to the 12. It maybe would give us a few-fold factor. So it's interesting, but not for this, not just for the order of magnitude. Okay, 10 to the 13 can also be written as 10 terawatts. Okay, tera is 10 to the 12. Remember, mega, giga, tera. Good, so 10 terawatts. One thing which I think is cute, or not so cute, but that gives you perspective, is this issue of, today with the need for dealing with carbon emissions and with supplying energy, there's a big subject of, new power plants, which one do you build, how do you build them, etc. So I think from that, the fact that we got a global value, we could connect it to the issue of how fast are things being built in terms of power plants, etc. So a way to think about it is if we need to produce if we're producing 10 terawatts of electricity, how many power plants do we need globally? Do we use globally? How much is one power plant roughly? Anybody knows how much electricity does a power plant produce?
A few hundreds.
Yeah, a few hundreds what?
A few hundred kilowatts maybe?
Okay, so let's take a few hundred kilowatts. Okay, how much does a person need? 1 kilowatt. So if it was a few hundred kilowatts, it would mean that every few hundred people would have a power plant. I don't think so. Okay, so I hear like a gigawatt. Let's think about a gigawatt. If a person requires a kilowatt, if you have a power plant of a gigawatt, to how many people could it supply electricity? So if I have 1 gigawatt power plant, and every person requires 1 kilowatt, what's the number of people this supplies?
1 million.
Yeah, giga is 10 to the 9, kilo is 10 to the 3, so 10 to the 9, 10 to the 3, so this is 10 to the 6 people. About 1 million. Okay, so that's the correct thing. So look how, people had different values in their head coming from somewhere. With a really simple sanity check, you can see, whether the units made sense, are we in the right ballpark? Okay, so indeed 1 gigawatt is a very characteristic value for a new power plant built somewhere. Okay, so if I have 1 gigawatt and 10 terawatt in total, I can infer from these two that the number of power plants is roughly 10 terawatt is 10,000 gigawatt divided by 1 gigawatt per power plant. So I'm getting about 10,000 power plants in the world. Okay, that's roughly what we have in terms of electricity production. Now, power plants have to be, we're using more and more electricity, so you need to, increase the production, and also we need to replace them every few tens of years. Okay, so we have to make this number every few tens of years, either because we're increasing the production or we're replacing them. So if every few tens of years we have to make that number, it means that the rate of new power plants, that's about 10,000 per few tens of years, which is about few hundred per year, which is about 1 per day. So every day we need to build a new power plant in the world, which I see some impressed faces, which was my intention to impress you. I think it shows this thing about, they make these statements of, also like some countries like, say China or India, which have, a big population and also under rapid increase in the production of electricity. So indeed, it's like, you have a few new ones every week. And when I first heard it, it didn't make so much sense. Like, I know that usually it takes like 10 years or more to get permits and to start thinking about building it and whatever. How come that, you have to build a few every week? Well, this is just what clearly comes out of the numbers. Okay, which again I think shows also the immensity of humanity. Okay, it's just like this thing that like we don't have this good comprehension of 8 billion, it's just like a huge, huge number. Good, so what do we have so far? We did this and this and this and this.
But isn't building 10,000 power plants every few decades assuming that we have another 10 billion people on the planet every few decades?
No. I see how intuitively you would think that, but there's two other ways to think about it. You could have the same 10 billion people, but the power plants have to be replaced every, say, 50 years or something like that. Okay, that's one thing. And there's another thing is that those people, the average consumption also changes. It doesn't stay constant at 1 kilowatt or maybe. Okay. Okay, so this is the power plant, so let's say this is about 1 kilowatt, this was just electricity, right? But we asked originally how much is a person using in total. And there was a comment here, does it include also other stuff, like what? Like
agriculture production.
So I could ask how much, it's called primary energy, which means the total energy that I'll be consuming. So what else requires energy?
Transportation.
So I have transport, mobility, let's say. Industry. Okay, so there's more stuff that requires energy. And also there's an interesting thing. If I need 1 kilowatt of electricity, in terms of primary energy is like how much, I have to burn in terms of total joules of, fuels or through solar energy, etc. I won't get the kilowatt directly. There's some efficiency of production of that 1 kilowatt. So to make things short, in order to get 1 kilowatt, I have to invest based on the efficiency, I don't know, somewhere between 2 and 3 kilowatts of primary energy of fossil fuels or whatever is the thing I'm using. Usually it's fossil fuels these days still. And for these things, it's also roughly of the same order of magnitude like what we need for mobility or for industry. So I have also a few kilowatts per person, which means that in total, if I take it for Israel, I would get roughly 10 kilowatts per person of primary energy. And now if I'll scale it globally, I would say times 10 to the 10 people. It would give me some value, but then if I compare it to, the total number, it would actually, again, come out to be lower because, the same comment that I got before, this 10 to the 10 people, this is all of humanity. But actually, the number actually, with not 10 people, 10 billion were 8 billion, and many of them are not consuming that level, so it would be somewhat lower, etc. But it gives us the right order of magnitude. Yeah.
When we use fossil fuel or any other kind of energy source, all of it turns out as heat, all the energy we consume. Like we are looking how much we eat in the planet by energy consumption, but not all of it turns to heat.
So we could talk about that extra effect. The vast majority turns as heat.
Oh.
Okay, so the vast majority turns into heat. Okay, so if I was doing that, this is 10 kilowatt per person times 10 to the 10 people. This would give me 100 terawatt. Okay, 10 to the 10, 10 to the 11, 10 to the 14, which is this. And if you actually check, it's actually coming to lower. It's about 20 terawatt because of those, many different effects on the population, etc. But then going back to the original question, how much are we heating the Earth? It's becoming a bit long. Let me see how I want to spend the time here. Okay. I'll do things kind of, some of it would be a bit fast, and if you want, you can afterwards watch it or try to derive it yourself if something doesn't make sense or you feel that it's going too fast. Okay, we have 20 terawatts, and remember we wanted to see this is the amount of heat that we're emitting. I'm telling you, most of it is turning into heat. How much is that in terms of heating the Earth? How would I approach this?
To check the mass of the Earth.
I can do the mass of the Earth. That's an interesting approach.
Maybe efficiency, because whatever doesn't go straight to electricity goes to heat.
No, he says that's all.
Okay, so it's already, I see, it's interesting because you have different approaches how to go about it. There's a nice way to do it, and that is when you want to talk about it in comparison to, say, the energy coming from the sun or the greenhouse gas effect, etc. It's talking about how much energy or power am I releasing per square meter. Okay, that's the flux of energy. Okay, and that's more relevant than, let's say, the mass of the Earth, because, I'm not heating the mantle. That would, take, thousands of years or whatever until it reaches, steady state conduction, whatever. So as usual, every lesson we have to have a map of the Earth, and we ask what's the area.
10 to the power of 9 kilometers square.
And by now you know that it's like 500 million square kilometers. Okay? 500 million square kilometers, that's 500 tera meters squared. Okay, that's the 500, and we had the million, but this was kilometer going to meters. It's twice 10 to the 3, so million giga tera. Okay, you can do the unit conversion to check me afterwards. Okay, so if I have the total power of humanity, and I have the total area of the Earth, I can do the power divided by the area, and it would give me 20 terawatt divided by 500 tera million squares. And what am I getting? 20 divided by 500 is like 2 divided by 50. It's like 0.04. Tera falls with tera. Watts per meter squared. Okay, so I just calculated how much is humanity heating the Earth just by the fact that we're using energy. I think that's really cool. Probably you don't think it's really cool because you don't have necessarily a context. Okay, without context, it doesn't mean much. So the question is whether you can dig in your head and find context to this value that we just got.
We know that the sun, giving to the Earth like 250 watts per meter square.
Fantastic. So we know that the sun that's hitting the Earth is giving us 250 watts per meter square. Good. So now we have some kind of context. So what do you think? Impressive or not impressive? Not so impressive, right? Like, okay, so it's impressive that we could get a number, but in terms of its effect, it doesn't seem to be much. Like it's 1, 2, 3, 4 orders of magnitude less.
Now we can take the heating of CO2.
Great. So let's talk about it in a minute. Okay, so in terms of the total flight, it's like 4 orders of magnitude less. Not so impressive. Okay, but then you're saying, let's take the heating of the CO2. What does that mean?
The greenhouse effect of only the CO2 component.
Great. So, like, we're not claiming that, like,
I'm not sure what you meant by that.
I'm not sure either. Okay, so we're not claiming that this is, we're replacing the sun or something like that, but maybe a more relevant context is to say the effect of human effects of what's known as like radiative forcing. Okay, it's a concept that's worth knowing the term. Radiative forcing. We don't need this. And this talks about the effect of how much, due to greenhouse gases emitted, how much extra is trapped out of the 250 watts per square meter. Somebody knows how much that is?
0.1 watts per meter square.
So why don't you, again, this is now, I took you really far from where you have intuition. So you can go back to your LLMs or ChatGPT and let's see if somebody could just ask, how much is the radiative forcing caused by humanity?
In 2019.
Okay, the question is relatively straightforward. How much radiative forcing?
Few watts per meter squared.
Yeah, good. So radiative forcing is about few watts per meter squared. The concept is clear. Like we're emitting things and therefore we're affecting this 250 watts that's coming. There's an extra bit that is kind of like trapped, which is on the order of a few watts per square meter. If anyone wants to know more, it's the physics of climate change, worth knowing in a warming world. But you can see that, like, okay, we don't need to, it's not that this number, is supposed to affect, the sun. We're talking about affecting how much is it versus the things that we're doing as a result of greenhouse gas emissions. And you can see what? Again, that this is now not 4 orders of magnitude lower, it's like 2 orders of magnitude lower, like 100-fold less. Just 1 second. So we see again that this actually effect of the heating, the direct heating, that's not a very big effect. Or the order of like 1%. Yeah.
But to get this number, the 0.04, you divide it by the total area of Earth. But most of the power plants are concentrated in specific areas, and in these areas like cities, this effect might be larger.
Fantastic. So let me repeat that. You're saying maybe because this energy that's being emitted is 20 terawatts, it's not being emitted homogeneously, but in specific locations, so maybe there you'll have a heating. So you're both right and not important. So you're right in saying it does happen there, but now the question is how much effect will it have locally? Depends on like the kind of like diffusion time or dispersion time or whatever time is relevant. And usually that would be dispersing. So usually, like say you have a power plant, much of the heating goes into the river or to the body of water. and that gets to mix before it gives like a huge effect. It is true that if you go out of Hedera, you get into the water, there's a place with like hot water and the sharks come and all of that fun. But that doesn't mean that like you will having, all of that heating staying there, but it disperses through the Mediterranean or whatever, and it becomes not a big effect. Also there's also the issue that, anyway, there's also the fact that it mixes with the water, so it's not exactly the radiative forcing. That's an interesting subject for discussion, but I don't have time for it now. Maybe somebody wants to do a final project on it. You're most welcome. There's all sorts of ideas here that you'll see could be relevant for such things, yeah.
No, I just have one thought that it's like the average thing might be problematic here because it's like the average temperature goes up like 1 degree. It always sounds like, okay, it doesn't sound like such a big deal. But in the end, the consequences are drastic. So I don't know how to put that into numbers, but there seems to be something with the average maybe that is problematic here.
Okay, so good point about average and whether things seem dramatic or not. So maybe a few things to say about it quickly. Let's say 1 degree, or actually we're now at 1.5 degree, and over land it's more like 3 degrees because it's significantly faster. Is that a big deal or not? So first of all, we could look into it and see that it has big ramifications, but maybe a nice analogy is to think, for example, on a person. So if I tell you, temperature in Celsius is 37 degrees, I tell you it's not a big deal. It's only 3 degrees more. So you go from 37 to 40 degrees. I don't know if you're alive. Okay, so it's like, it turns out that, things that, whether they're a big deal or not, we have to know the physiology of the system, etc. And so it's one thing to remember about the effects of climate change. And maybe a nice thing you could say about it, so this extra few degrees, this is like not accurate, but just to get, so this out of that, the effect of humanity through climate change versus this is about 1%, right? Okay, the temperature of the Earth, how much is the temperature of the Earth?
25.
Is the surface?
300 Kelvin. Okay, you have to think in Kelvin because that's the relevant unit here. If you take 300 Kelvin and you perturb it by 1%, how much of a change is it?
303.
3 degrees. 3 degrees Kelvin or 3 degrees Celsius, which is on the right order of magnitude of what we're talking about in terms of the effect. Okay, so in an interesting way, you could tell me, you just change it by 250 to 253. Who cares? No, so you do care because, we are as sensitive to these things when you think about it in the relevant units. Anyway, it's much, much more complicated, black body radiation, all sorts of other things. So, I'm not Stefan Boltzmann. Don't get me that I'm not summarizing everything that you need to know. Okay, so we got it versus climate change. Okay, so the thing I want to tell you is like how with numbers, say we started with just a few numbers there, 1 kilowatt or something like that, you can infer all sorts of things. So we infer things about climate change. Let's also try to infer more things about other domains of life. So one thing would be about how much carbon emissions are associated with this. So let's see how we could do that. So what am I asking? We just said that every person is using some amount of some amount of kilowatts, right? And I want to convert it from kilowatts into kilograms. Kilograms of what?
CO2.
Let's say kilograms of CO2. Or CO2 equivalent, it's like, maybe there's some other things there. How do I do that? That's a challenge because it's not, one is kilowatts, one is kilograms.
Was the calorie again? Yeah.
The calorie again. You weren't as excited as I was hoping. The calorie again. The calorie again. Yeah. So yes, so this is some energy in it, and the calorie also has some energy in it. So there's something that's supposed to connect it. Okay, so I have a challenge here. I need to connect from some type of unit to a different type of unit. So there's a way to go, and that's like following the units. Okay, so I'm interested to know. I want to get something that in the end will be. Just 1 second.
I think 1 Newton is the same as.
Give me a chance. Now I need to. Okay. Kilowatt hour, kilogram of CO2. Okay, this is like the units that I want to get to in the end. Okay? You probably want to know kilogram of CO2 per kilowatt hour, so it doesn't matter. You can always, do the inverse. Okay, the question is, what do I have to start with? Okay, and so somebody said it correctly. I know something with calories. Okay, so what do we know? Calories is nice because that's units of that we know of. And let's say we're talking about what creates those emissions, fossil fuels, right? So I need to know something about the fossil fuel and to know how much energy there is in there. What do we know?
Density.
Yeah, we know the density of energy in
Oil.
oil. Oil is pretty good because that's actually represent a very relevant fossil fuels. So there I know how many calories or kilocalories I have per kilogram of oil. Okay? Anybody remembers how much?
90?
Yeah, 9, so let's make it 10. And this is per 1 kilogram of oil. Okay, it's actually per liter, and liter is a bit less, but we're doing order of magnitude, so we don't care about those small effects.
It was for 100 grams.
Okay, so, excuse me, that's per gram. Thank you, you saved the world. Okay, we would have gotten into a big problem in the world otherwise. Okay, so this is per gram of oil. I would have found out eventually, but okay. So now here's the thing of how you go from the thing that you know to the thing that you want in a few almost easy steps. Okay, it's not that easy, but it will take us a bit, but with time it becomes pretty easy. Okay, so you could do it by two things. You follow the units, and you know that you're always allowed to multiply by 1. Okay, there's nothing bad in multiplying by 1, and that gives you the way to go from one way to the other. Okay, so how do we go from this to that? So we need to convert kilocalories into kilowatts hours to connect between this and that, and we need to connect between gram of oil and kilogram of CO2. Okay, so let's start do the job of moving from here to there. So the kilocalories, I don't like kilocalories now, I want to get kilowatt hour, so I have to go from the kilocalories to the joules, right? So let's see how we do that. So I can say I have like 1 kilocalorie. What do I know about joules? I know that every calorie is about 4 joules. You remember that, we talked about it last time, and this is 1,000, so this is 4,000 joules. Okay, so far so good. Not so complicated, right? Okay.
You've got the kilo at the end though, so maybe it would be easier not to do the 1,000, the kilocalories.
Yeah, so okay, so
K
good.
there and K there, just
Good, so you're saying I have the gram and I want to go to kilogram, right?
no, the
kilowatt.
like kilocalorie to kilowatt hour.
Yeah, but don't it would be okay. Like, okay, well, if you really want to do it now, you can say, okay, you want to go from joule to kilowatt hour. So I could say 1 joule, I want to write how many kilowatts hours there are, right? But that's tough because 1 joule is very few kilowatts hours. So it could be nicer. Look what I could do. I could just say 1 kilowatt hour, and I can write here how many joules it is. I'm also allowed to do that. Okay, so how many? So we know it's a watt. Watt is not a problem. But I have the kilo and the hour. Kilo is 1,000. Hour, in terms of seconds, is
3,600.
3,600. So actually, you could derive it yourself. This is like 3,600,000 joules. Okay? Good. This is what you wanted? Yeah, you got it.
It's the same, yeah.
You got it. Okay. I think we're getting close, right? Because this is kilocalories. Good, gone. Joules, gone. So I just have kilowatt hour, which is what I need in the end. That's fantastic. But I already have one, I still have one big problem, and that is that here I have gram of oil, and here I have kilogram of CO2. Okay?
You burn it and then the weight of it increases because of the oxygen.
Exactly, so we'll do that in a minute. So let's do the easy part first. Okay, I have 1 gram of oil, and I want to go to kilogram. Let's say first of oil. Well, that's easy. 1 kilogram of oil is 1,000 grams of oil.
Yeah.
Okay, so I'm only left now with kilogram of oil going to kilogram of CO2. That's the tougher, excuse me for a second, that's now the tougher part. You have to think for a second. It's not just unit conversion. How do we do that? We think about what's happening. What's happening? You're taking this oil, which you know is like CH2, right? Or let's do it this way. Oil is something like, it's units of this, and you're adding oxygen, and you're getting CO2. Right? So for every kilogram of this, how many kilograms of that are you getting? This is the thing that was that Evyatar is saying. We could look at the molar weight of this is like 12 and maybe plus those two, let's say 14. And we're converting into this that has 12 plus 16 times 2, 32, 44. So this is 44 Dalton, and this is 14 Dalton. So going from here to here, you kind of like triple it. Okay? Which means that for every 1 kilogram of oil, you're getting, let's say, 3 kilograms of CO2. Okay, this was the toughest, more like, intelligent part of the whole thing. But the nice thing is that, okay, kilocalorie felt with kilocalories, joules with joules. I have kilowatt hour, gram oil with gram oil, kilogram oil with kilogram oil, kilogram CO2, exactly what I needed. So I only need to calculate what comes out of all this mess. Okay, so let's see. I have 1,000, 4,000, this is 4 million, which is kind of like this 4 million. Good, so I got rid of this, this, and this. So I only have 10 and 3. So I'm just getting few. Let's write it here. So this gives us few. What are we talking about? Kilowatt hour. Kilogram CO2. Okay, which is equivalent to saying, point few kilogram CO2 per kilowatt hour. So I just got the universal conversion from energy into greenhouse gas emissions. Which again, if you're not impressed, maybe you're in the wrong course, but I think it's pretty neat. And also the fact that I did it, just by, I took my time to do it, but you're getting used to it or whatever, or you can just, so we're getting a conversion stick to do from this to that. Okay, why is that neat? Let me show you like real quick, because now if you have just this, you remember we said that every person, if you go back to what we had before, we said, we're using electricity about 1 kilowatt, but let's say together with all sorts of other stuff, let's say in Israel, you use about 10 kilowatts in total. So if you have about 10 kilowatts, and now you want to see, okay, let's say let's take like a normal person in the world. So this was, we said, because of the global south and every other, let's say it's just few kilowatts on average. So that means that if I'm emitting for every kilowatt hour, I'm emitting point few kilograms CO2, it means this times point few kilowatt hour, kilograms CO2 per kilowatt hour. I'm getting from this that I'm emitting about 1 kilogram per hour few times point few. So every person on Earth is now using or emitting about a kilogram per hour. Or if you want to look yearly, how many hours do we have in a year? Exactly, 8,500 blah, 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 10,000. It's also a nice number, nice round number to remember, 10,000 hours in a year. So that means that if I'm multiplying it by 10,000 hours per 1 year, again multiplying by 1, I'm getting about 10,000 kilograms or 10 tons per year.
Per person.
Per person. Which is also a pretty neat number to know. 10 tons is roughly the emission resulting from a person every year, which is a heavy load. By the way, if you think 1 kilogram per hour, it means that you're emitting, your weight in carbon every
2 days.
Every few days.
Few days.
Depends how much you weigh, but in any case, it would come out to few days. So every few days, that amount of carbon, I think quite staggering. Finally, to show like what you can achieve with this, so we did this and we did this. We're getting to the end of this hour. So if you know that you are emitting about 10 tons per year, you can try and say, okay, what does it mean in terms of money? How do we go to money? So, numbers could enable us to do everything, or not everything, but a lot of stuff. Can you connect it to how much?
Like how much, like the oil price?
Not the oil price, but let's say the cost of abating climate change, or if you want to do carbon storage, or taking that carbon, or the cost of how much you emitted in terms of say if there's a tax on carbon or something like that. So you can also do that conversion. For that, you just need to do something that would give you a value of dollars per ton. Anybody knows anything about the cost for carbon? Okay, so you can ask your favorite thing, and you'll come out that usual numbers are between $10 and $100 per ton, which means that you can take this and also convert all of that into units of money. Great, so I think we achieved quite a lot on energy. So I want to send you to the break with one question to keep, just to try and test your thinking about the world. And that is the following. One of the things that requires the most, this is the most intensive in terms of production, in terms of carbon, is what's known as smelting of iron. Anybody knows what smelting of iron means? It means whenever you want to make steel for construction, for other stuff, you take iron ore, which you dug something somewhere on Earth, you do smelting. Okay, like you heat it up, you do whatever, it becomes molten, and then you can make steel out of it. You need to put some extra stuff, etc. Okay. The question is the following. For smelting of iron into steel using energy. So I want the energy to run it. Let's say I'm just taking it out of sugar. Okay? How much mass of sugar do I need to extract energy, like to burn, in order to give me to run the process of taking iron and turning it into steel? So using energy from sugar, per 1 gram of iron. And the question is, do I need A, 1 gram of sugar, B, 1 kilogram, or C, 1 ton? Okay, I'm sorry, I was not so clear in my head, so I'm starting again. I want to take iron, turn it into steel. For that, I need to heat it up, do all sorts of stuff. Let's say I want to run it. We're just using the energy that's in sugar. The question is per gram that I want to convert from this to that. Do I need the energy from a gram of sugar, a kilogram of sugar, or a ton of sugar? Okay, I'm making it easy, so it's like, 1,000-fold between the options. Okay, we'll do that after the recess. You could, you could think about it during that time. But just to check your intuition, who thinks it's about 1 gram of sugar? Only me. 1 kilogram of sugar? Half the class. 1 ton of sugar? The other half of class. Okay, good. So let's take a 10 minutes break. You keep on thinking about it if you want. Make some the sugar levels in your body work, and we get back. Okay, we're back at smelt. Just before we go back to smelting iron, 2 things that came in the break that I think worth mentioning. One was, you remember we had this value, 10 ton per, or we had it equivalently, it was 1 kilogram per hour. And Misha was asking me, what about the emissions that are coming from the food that we eat? Right? Because each one of us is eating food. That food is being turned basically into carbon dioxide. So how much is that versus this? Okay, so how can you do it real quick? We know that we're eating how much every day?
2,000.
Yeah, 2,000 kilo. But going to mass, I think we prefer mass units now. About half a kilo. Okay? That half a kilo, I would say about a quarter of it is half a kilo, about half of it is carbon. Okay? So half of a half, we're eating about a quarter of carbon per day. Okay? And now going from carbon into CO2, how much is that? It's about a factor of 4. You can do it's exactly the same calculation. You're 40 something Dalton from 12 Daltons, about 4. So a quarter of a kilogram per day of carbon is 1 kilogram per day of CO2 emissions from our food. Which means that we're emitting every day what on the average, the overall is about per hour, 1 kilogram. So it's about order of magnitude, somewhat more or less. Okay, from our food, we're emitting 1 kilogram per day, but from our overall CO2 emissions, we're emitting 20-something kilograms per day.
But that's just like the breathing, right? That's not the whole food system.
Yeah, right. That's just the question was directly about the food that we're consuming. There's also the extra things in the production and things like that. We'll talk about it maybe also in a few minutes. Good, so that was one comment. The other comment or question was about the usage. We had this nice algebra that we introduced in the beginning of the class, 1 few 10, and you can see I'm using it quite a lot. And on the other hand, I'm sometimes using, 2 and 8 and 5. And the question is, when do you use this and when do you use that? Okay? So the answer is that, usually, not, mathematics have this, real decimal system and you're using with usual numbers. That's what you probably want to use when you're doing a thorough calculation. The 1 few 10 is when you want to do street fighting mathematics, like, when you just want to derive something very crudely and quickly in your head or on a piece of paper, so you can use that. And here I'm sort of like, I'm using both methods. Okay, sometimes I'm doing like something really crude, sometimes I'm doing it a bit more accurate, and I'm jumping between them. I'm sorry if it's confusing. The reason I sometimes, not doing everything 1 few 10 is first, I sometimes want to do it a bit more accurate. In some things I would just feel bad about myself, about, some of those things here. When you do 1 few 10, you can easily get a factor of a few wrong. And let's say if I calculate it for the cost of electricity, it becomes, like a gigantic number. It could be like, I feel uncomfortable about myself. But in general, I would say you use this for that and this, when you have time, you do it properly. If you want to do just roughly, you can do 1 few 10. Okay, so we talked about that. Let's go back to this. I remind you, half voted for this, half voted. Anybody wants to change their mind?
About the topic?
Not about the topic. You can also change your subject about the topic or the course that you chose. You can change the course. But on this specific, so you want to change your mind?
Change to 1 gram.
You want to change to 1 gram? What a surprise. I gave you a hint that I voted for 1 gram from the beginning. Okay, why would we say 1 gram or any other value? So it would be useful to go back. So, what did you have in your mind, right? Like you like smelting iron, you have to heat it up a lot. Okay, let's see how much heating can we do with 1 gram of sugar? Okay?
Calories.
Yeah, the calories again. So how many calories do we have in 1 gram of sugar?
4 kilograms.
Exactly. So 1 gram of sugar is roughly 4 kilocalories. Excellent. If I have 4 kilocalories, what can I do with it?
Transfer to joule.
I don't want to transfer it to joule. I have 4,000 calories, right? And the calorie, by definition, allows me to heat, let's say, 1 gram of water by 1 degree Celsius. So if I take the energy that I have in the sugar when it's being oxidized, I can heat the sugar, the water, the iron by how much? If everything has the same energy, heat capacity, whatever, which is actually okay. By how much?
4,000.
4,000 degrees. Okay? So even if for doing the smelting of the iron, you have to go to 1,000 degrees Celsius, 1,000, 2,000, I'm not sure what's the exact value. Maybe somebody checks and tells me.
1,500.
1,500. Okay, so that's easy. Easy, I can do 1,500. I can do 4,000. Actually, the heat capacity is less. Water is like a lot in heat capacity, so it's even more. So the answer is 1 gram. Which I think is interesting, both because, I tricked you by a factor of 1,000 or 1,000,000, but it also shows again how our intuition is sometimes wrong and how we should try and improve it. Again, without the need for something, I didn't need to build like a model of smelting or something like that. I just need to think, clearly about those things. And I think it also connects all sorts of things in an interesting way because like this thing like sugar, we think about it somewhat as like, like a harmless thing, you just add it to your tea or coffee. You don't think about it as something like thousands of degrees of whatever. But it's like, and the way to think about it, like for example, you can think the fact that you can burn it. What does it mean you can burn it?
It oxidizes?
Yeah, but when you burn it, it turns into, fire, which is, easily a few hundred degrees, or in the center, much more. So it has that capacity. So it shows you that actually it is extremely energetic. In a way, between that and, oil that you put in your car and runs your motor with, it's only like a factor of 2, right, in terms of content. 4 kilocalories, 9 kilocalories, whatever. So it's all the same in terms of that. It's like just very, very energetic. We just don't think about our food in those terms, but it actually is. Okay, so I thought that was worth pointing out. And to connect it all, and this would be our final module for the course, I have a dilemma for you. So I'm guessing some of you come here or to work, and every day when you wake up, you say, how would I go to work or to the lab today? I have two, let's say, if I care about what's happening to the earth in terms of carbon emissions, do I do my commute with a car? Or do I do it some other way? Let's say, I take the bicycle or I walk. And the question is, what has more CO2 emissions?
I think you need to add the time dimension.
Car or bike? And you want to make, so how far do you need to commute? So let's make it realistic, right? Like what?
30 kilometers.
Yeah, 30 kilometers, it's pretty tough. Let's just make it, let's say you just live in, I don't know.
10 kilometers?
Not that far away, so let's make it 10 kilometers. Okay, but let's make it, 5 kilometers this and 5 kilometers there. We do 10 kilometers, then we could scale it to any other thing. What do you think?
Interesting question.
We can do the same calculation we just did because we know the oil consumption of a car.
Yeah, so we could do that in a minute. I heard somebody say something, tricky question. Okay, so why, obviously I think, all of us, have, the answer, you have much more emissions with the car than with, say a bike, right? So why is it a tricky question?
Because when I'm sitting in the car, I'm not consuming energy, but when I'm riding a bike, I need to burn calories. Yes.
Okay, so this is the trick. Why is that a problem? Why do you mind? Many people want to burn calories.
It emits CO2.
Okay, so right, so if you bike the bicycle, it depends exactly. If you just if it's any calories you need to burn anyway, go ahead and burn them. But if as a result of that you get to work or to Weizmann, then you go and eat something, you bring back those calories. The question is how much CO2 would be emitted as a result of you eating those calories. Okay, that's the trick. Or not the trick, that's the reality. It's just usually we don't take that into account. So let's do a calculation to try and deal with that. Okay, you can do it in the final exercise, but
we still get hungry when we drive the car. So.
That's a correction I don't have a calculation for. You can do it in the final exercise. Okay, how hungry do you become from driving a car?
Actually, there's like a good point here that most of the calories that people burn, you burn just to stay alive, and like running or riding a bicycle or something is like a minority of that.
Yeah,
okay.
10%.
So there's actually a good point there. You do get hungry. Like a large percent of you getting hungry is from sitting.
Fantastic. Okay. So to be clear, okay. So on the one hand, I think the point you're raising is this basal level, basal metabolic rate, and that leads indeed to some calorie consumption that's on the order of like just below 2,000. That's just like if you were sitting sedentary, I think it's called like just sitting at your desk doing nothing but playing video games or whatever, or not playing video games, and how much calories. So okay, that's true. That's a bit okay. Now we're talking about the fact that you're doing exercise beyond that, and we're talking just about this extra bit. Okay, and this is what we'll be analyzing. So no trick in that respect. We're talking about the extra, and so this thing of just driving in your car, but that's just the basal level. We're talking as a result of extra exercise. Okay, and then just 1 second. There was another comment I wanted to make. Yeah, and then on the other hand, whether it adds or not, you can ask the people doing the Tour de France, and they're eating a lot more. Yeah. Okay, so it's not like it's always negligible.
Yeah.
Okay.
But
they do a lot. Yeah.
Kind of, if you're biking, you're kind of engine for bike. So we can just maybe compare, the job is actually to move the bike from one place to another. And the same stuff is car. So maybe we just can divide the mass of car by mass of the bike, and then it would be the same rate of energy. I mean, if
I get it.
car
Okay, so
weighs 10 times more than bike, then it should consume 10 times more energy at least.
Fantastic. So I think you understood the idea of to do it scaling by the weight of the stuff. And so let's do a calculation, and then we could revisit that, or you could revisit it. Yeah. Okay, so let's go ahead and do it. So I think let's start with the car or with the bike? Good, we'll start with the car. Okay, so let's start with the car. Although you're right, it's bike is the more interesting part, but so I need to go so I want to go 10 kilometers, and I need to know how many emissions would result out of that. Okay, so if with the car doing 10 kilometers, and it depends on how efficient my car is. Okay, like how much gasoline, let's say it's a gasoline car for now. If you want to do a different car, make it your final project. So how many liter would I need?
1 liter.
Yeah, so like a not very good car is about 10 kilometers per liter. Okay, kind of like an older car. Order of magnitude, it's okay. Okay, so now I need to do, again, like all the unit conversion. So 1 liter, let's say it's 1 kilogram of oil. And to go from oil, 1 kilogram of oil, what do we know about how much CO2, kilogram of CO2? Few, right? We just calculated it in the last half an hour. So altogether, I'm getting
Fuel.
10 kilometers, few kilograms of CO2. Right? The units are fine. Okay. So you could also see, by the way, it's like 0.few kilogram of CO2 per kilometer. Just like as when you're going with a car, and we know it just emitted this.
Yep.
Okay, that's why I wanted to start with the car. Straightforward. Yeah. Okay, now the bike. How do I do it with the bike?
How many calories do you burn?
Calories again. Okay, yeah, that's a good idea. So I want to know how many calories would I be burning as a result of biking? How many?
Hundreds?
Okay, good question. Maybe somebody has it in their head. Probably you don't have. So let's again, if I needed to solve this problem, I would go and ask ChatGPT or the like. So why don't you go and try to do it right now?
I'll wait for I have it in my wallet.
Okay, so you don't do it. You take it from your wallet. They take it from their ChatGPT. How much would it? What are you getting?
200.
So notice that it kind of depends what kind of a biker you are, right? Like there's biking really fast, really slow, whatever. So I would ask you to give me an answer on like the speed at which you go, and how many calories. What's the rate of calorie consumption? It's like two numbers. You need two things in order to get a proper value. Okay, is there something, because it would, okay, so this is not bad, but just, is there something that just tells me, the speed and the rate?
The speed was 7.8 kilometers per hour.
Okay, you take it from your watch. I don't know if everybody has that watch. So let's take from something that's more easily available to everybody.
Relaxed city ride is 300 kilocalories.
So relaxed city bike sounds fun to go to work, so I'll take it. So 300, what?
300 kilocalories.
For the
entire ride,
for the 10 kilometers.
Yeah.
300 kilocalories per 10 kilometer.
Yeah, that's what it says.
And that increasing depends on your weight. That's what ChatGPT.
Yeah, so I think the numbers I have in my head that I think I got from ChatGPT was, I think, 300 kilocalories per hour when you're going at a rate of 15 kilometers per hour. Okay, let's just see if this fits with that. Not so well. Roughly well. Okay, it's not so bad because this is roughly okay. Notice by the way that like one thing maybe you want to know. So this is like if you're using this, 300 kilocalories per hour, that's what you're burning. You probably want to do it in comparison. You want to take this issue of like the basal metabolic rate that we're saying we're using some calories anyway. So if in that hour you weren't biking, you would have been sitting or doing what? And this also burns some. What is the basal metabolic rate?
200 per hour.
About 100 per hour, right? Because it's 2,000 in a day, 24 hours. So 2,000 divided by 20 hours, about 100. So it's really kind of like effectively the extra calories, about 200 kilocalories per hour. And 200 kilocalories per hour for 15 kilometers less. So you get out of this about 10 kilocalories per kilometer. Okay, I'm dividing this by that. Which is, it's not exactly, I don't know, we need to see how this came about. Maybe this is for like really tough biking where you're emitting more. Okay, so what do we do from here? So we have how many kilocalories extra. So we say this is for kilometer. So overall we know we have an extra 100 kilocalories invested in this biking. But I want to go into CO2.
So we know the weight of food. We need to think of the weight of food we need to eat in order to consume 100 kilocalories, and then convert food to CO2.
Okay, so this is okay, but this conversion would say how much CO2 was emitted from our food. This is kind of like what we were doing before, but that's not the only emission of greenhouse gas coming. It's not just the food itself that's being emitted. It's also or the greenhouse gases associated. It's also the greenhouse gas associated with the production of the food. Right? So we have to think about what is, we need to have now something about saying how much kilogram of CO2 per kilogram of food. That's the magic number that we need here.
But we didn't implement the car, like how much the production of the car or whatever.
Okay, so you could ask about the production of the car. Good, you can also include that. Usually for cars, after you'll do the whole thing, usually the major emissions from a car is the use phase, is the usage phase. It's like the time, is using, there's an extra thing for the production, but when you do it over the lifetime of the car, it's a small fraction, relatively small fraction. Okay, also here, the equivalent, I didn't take into account the greenhouse gas emissions for my parents making me. I only, it wasn't like the production of the person. It was just like talking about the production. It was really the fuel. I'm just saying it's not the fuel directly, it's also the production of the fuel. Anyway, going, what?
So it's also not what is required to produce the bike. It's just what's required to
No,
power
I was wrong. I tried to make I was wondering why we now implement the energy needed to food, and was trying to find the equivalent in the car example. So it would be actually the energy needed to produce fossil fuels.
Exactly.
Yeah, so
okay, and the fossil, and the fossil fuels, somebody made it for us millions of years ago, some plants or something else.
No, to get it out of the.
Okay, so we need to know that value. I actually also have a cool way to derive that, but we don't have time. So, again, I could leave it for somebody who wants to see how to derive such thing from, basic principles or things you can have intuition for, etc. So it's a nice challenge for a final project. But what you can also do is try to ask, ChatGPT or something else about, find a paper that gives those values. And the short answer, it's something like 0.few to a few, to blah, blah, blah. 0.few to 1 kilogram of CO2 per kilogram of food. This is like when you look at like staple foods, like if after you finish the bike, you go and you eat oatmeal. Okay? But it would be somewhere between 10 to a few tens of kilogram CO2 per kilogram of food. By the way, when I'm saying food, it's like food dry. Okay? Or something like that. This would be for staple food. And this would be for, say, beef. So it would be significantly higher. Okay, so again, I'm not deriving this, but you can get it relatively easily. So if I take this value and I'm plugging it back here. Aha, just 1 second. Okay, so it's a bit tricky because I also need to say, I need to go to, there I need calories. Okay, so let's see how the best way. Okay, so let's say 100 kilocalories. I can convert that to how much food I need to eat, right? For 100 kilocalories, how much food do I need to eat?
25 grams.
Yeah, something like, say, 25 grams of dry food. Again, I don't enjoy eating dry food. Okay, we could add as much water, make it like with a nice sauce and everything. It's just in order to do the energetic efficiency and energetic stuff. Okay, so if I'm taking a value of say 1, I'm taking the upper, or like this, okay, so few tens, let's make it. Or let's say we need it in kilograms, right? So it's 0.0 few kilograms. Okay, the 25 grams is 0.0 few kilograms. Times this, I'm getting that in terms of CO2 emissions, it's between 0.01 to 0.0 few kilograms of CO2. This is in comparison to the car that gave me this per kilometer, that for 10 kilometers I got few kilograms of CO2. This is for the overall 10 kilometers. So we see this is about 2 orders of magnitude less.
Did you take into account also the CO2 from exhaling?
I didn't. We could take it. I think it wouldn't be a lot. Why do I think that? Or maybe I'm wrong. Let's see. 25 grams of dry food, blah, 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 blah.
75.
It would be of the same order of magnitude. Let me see if I got something wrong. So maybe it would be of the same order of magnitude. So maybe twice that or something like that. Okay, it wouldn't change your orders of magnitude. Okay, but by the way, notice that if after you finished your bike ride, you fill up the calories back by eating beef, which is about almost 2 orders of magnitude more, it means that now you're kind of like, it's as if you were driving a car in terms of like the greenhouse gas emissions.
Okay.
So you can be either vegetarian and take a car, or
Okay, I didn't talk about giving you moral license based on this or that. But we could also ask, other interesting questions. What if instead of a bike, let's say I was walking, what would be the result of that? Because is it more efficient, less efficient? It turns out that if you, anyway, you could play around with it, but it's, let's say bike is way more efficient than walking. The question is quantitative, how much and how would that compare? Or you can ask yourself, what if instead of taking a bike or a car, let's say, I don't like taking, doing all the extra activity. I'm not sure if I have a shower or do not have a shower next to where I work. So I want to take something else that would not make me exercise so much. For example, an e-bike.
Scooter.
How much would that be in terms of greenhouse gas emissions? So how do we do that? Anybody has an idea?
How much does it take to mine lithium?
You need to check the power of the electric bike.
Right. Anybody has an electric bike and know how much power does it use?
How long do you charge?
Okay, so if you, next time you go to a e-bike, I also didn't know that, but you can ask ChatGPT again if we have the time, and it's about 100 watts for an e-bike. Okay, and then 100 watts, which means that you require 0.1 kilowatt hour per hour. You see what I did? I did a funny thing because I remember that I have this kilowatt hour because turning this into CO2 is tough, but I remember I had a law for kilowatt hour. So I just said this is energy, it's kilowatt hour per hour, which is just 0.1 kilowatt, which is 100 watts. Okay, and what do we know about the CO2 emissions of producing 0.1 kilowatt hour or a kilowatt hour? What was the value there? 0. Few kilogram of CO2, right? So I remind you, 1 kilowatt hour was resulting in 0.1 few kilogram CO2, which means that this would require 0.0 few kilogram CO2 per hour using your bike.
Which is the same as very normal.
So how much distance can I cover with that?
25 kilometers legally, let's say.
Legally. Okay, so everything we do in this course is legal, except for maybe some tricks that I'm doing, but I don't think I'll get into too much of a big trouble, but surely don't go above the speed limit. So in that 1 hour, I would get 0.0 few I would pay in terms of kilograms of CO2 that, and I would go, say, 25 kilometers, because this is how much kilometers I'm getting per hour. Okay, so if now you compare this into the regular bike, it's kind of the same, maybe even better. If you compare it to the car, it's much better. So clearly it's better to go with the, like if you want to do better in terms of your greenhouse gas emissions, to take the e-bike is much better than going with the car. And interestingly, it might even be on par, maybe even a bit better than going on the bike, but it's not as much fun and it's not as healthy. Okay, so clearly, just to be clear here, there's different metrics for things. Here we're analyzing CO2 emissions. There's all sorts of other things to take into account as health impacts and other stuff. So I want you to make sure that like you see the big picture. But it doesn't change the fact that we were able on pretty basic tools and things to derive things on questions that we might be interested on a daily basis, relevant to policy, relevant to life, etc. Which was our objective here, both in this example, in this lecture, and in this course. Okay? So before we end, let's see if people have comments, questions, demands, things about this. And we also sent each one of you, and I want you to open it either on your phone or your laptop or whatever you have, request for a feedback on the different examples that I gave in the course. So what we do every year is that we take, so you can open it in your whatever things that you have. We're getting feedback on the different examples or modules, I call them, that I'm doing in class. Every class I had about 3 modules. In 5 lessons, I had about 15 such modules. And we want to make sure which one of them really, you felt taught you something. So either, they kept in your imagination, you kept thinking about them, or told all of your family about it, you wrote in the social post about them. If you haven't, maybe you do it. And which ones you didn't understand what was the point, now that you think back of it, why did I waste your time? So we want to get that. So let's spend 5 minutes, you open it and filling out that, and we'll be using it as quickly as possible. Okay, so I let everybody finish that up. I'm putting some music so you can enjoy while you're doing that. It's also a good opportunity to say thank you for listening. We have the final project starting not next week, but the week after. We're giving you a bit of time to relax. And if you have any comments, things you're trying to decide what to do, how to do, etc., you can write us or come and talk with us. We want it to succeed. Make sure that you follow the procedure, meaning, you're finding somebody who helps you as a mentor. You run it on them, you verify how you're standing with time, with ideation, with understanding. If not, you can do it, you can change subject, you can try again. Just be sure you are ready on time. And we'll be really nice to you, don't worry. During the class, everybody will be friendly, and we'll try to support you throughout. And be sure not to go beyond the speed limit. Okay, we do everything legal. Yes. Yes. So write us the subject, so we give you approval. If you want to talk about it, you can talk quickly add or quickly or. Yeah. Okay, those who finish, thank you very much. And I'm waiting to see you in 2 weeks. Those who want to talk some more or finish filling it, stay with us and with the music and company. Bye-bye.